Hello and welcome to the KCSE Physics Paper 2 of 2012, the complete marking scheme. And we go straight to the first question. In this question, we are told that figure 1 shows a plane mirror XY. Is a plane mirror XY placed equidistant from two parallel lines AB and PT, AB and PT. So there is a mirror. There are two parallel lines which are equidistant, meaning that this distance is equal to this distance. This question is of course about the concept of reflection, but let's see what we've been asked to do. 4 students stand at P, Q, R, and T, P, Q, R, and T in front of the mirror. Of course, we know that their images are going to be formed at a distance which is equal to the object distance. For example, the image of R will be formed at a distance equal to this distance but behind the mirror. And you see they have already given us this line here so that we can know that the images of these students P, Q, R, and T will be picked up along this line. And the line which joins the image which is here to the object makes 90 degrees with a mirror. These are some of the factors that you need to consider when you're answering this type of question. Now indicate the positions of the images of the students Q, R, and T on line AB. So Q, the position will be formed here. R, the image will be formed here. And the student T, the image will be formed there. So you can see the factors that I've used. 1, the image distance is equal to the object distance. Number 2, the line that joins the object to the image makes 90 degrees with a mirror. B, state which of the 3 images are visible to the student standing at point P. So this student who is standing at point P will be able to see the images of student Q, R, and T. So we are asked to state which images are visible or which images can be seen and which one cannot be seen. Of course, the student will be able to see the image of student R and T. But by construction, if we were to construct ray diagrams for student Q, I doubt whether the student will be able to see the image of student Q. Part C, using rays indicate on the figure how B above is possible. So let's go to the next slide where you will see the answers that we've given here. So here we have it. Q, the image will be formed at this point, Q dash, this is the image of Q, this is the image of R, and this is the image of student T. Now, how does this student see each one of these images? Rays of light travel from point T, strikes the mirror at this point, and then they are reflected to the student at this point. So at this point, we can be able to draw a normal, identify this at the angle of incidence, this is the angle of reflection, and we'll be able to see as if this ray of light is coming from here, and of course that is where the image is going to be formed. But when it comes to Q, let me see whether that one is possible. It moves like this and then it gets reflected like this. So it's possible to see the image of student Q, R, and T, and you can see that all of them, once I've determined the position of the image, I just need to draw a straight line from there all the way to the eye. I'm going to dot this line here because these rays are virtual, but this is going to be continuous, showing that this is the incident ray, this is the reflected ray. So it's possible to see images of student Q, R, and T. But if this mirror was up to some point here, we will be able to see that it's not possible to draw a line from here all the way to here and that it is reflected by this mirror. This ray is reflected just at the edge of X. So it is possible to see the image of student Q. And let's go to question number 2. In question number 2, again, it's about reflection. What are we told in this question? Figure 2 shows two mirrors, PQ and QR. PQ and QR inclined at an angle of 110 degrees. A ray of light is incident on mirror PQ at an angle of 60 degrees as shown. Of course, this is the normal. We expect that there will be a reflected ray here and the angle of reflection will be equal to the angle of incidence. This is the angle of incidence. It's always important to try and identify each one of those angles so that you can use the first law of reflection. So we are asked to complete the ray diagram to determine the angle of reflection of the ray in the mirror QR. And I've already drawn this, so let's go straight to that slide and we look at it. So, like I've just explained, this ray is going to get reflected at this point of incidence where we've got the normal. This is the angle of incidence. The angle of reflection will also, of course, be 60 degrees. And given that this one is 90 degrees, we subtract 60 from 90 to get an angle of 30. Now we know that the angles in a triangle add up to 180 degrees. So this plus this gives me 140. We subtracted that from 180. We get this angle to be 40 degrees. And again, since we've got a normal here, this is 90 degrees. We subtract 40 from 90 and we get the new angle of incidence at the second incident point as 50 degrees, and therefore the angle of reflection at mirror QR is 50 degrees, and that is our answer. So remember to show the direction of these rays. When you draw ray diagrams, make sure that you show the incident ray or the reflected ray, and you must include the arrow. The next thing you must do is to identify the angle of incidence and the angle of reflection at each point of incidence, like I've done here. The angle of incidence is given, so it's up to me to use the laws of reflection and know that the angle of reflection is 60 degrees. At the same time, at the second point of incidence, I have to identify the angle of incidence as 50 degrees, and by using the same law, I get the angle of reflection as 50 degrees. You can see that when you follow these rules, questions become very easy. Let's go to question 3. What do we have here? We are told that figure 3 shows 4 identical light bulbs connected to a 15-volt battery whose internal resistance is negligible. So this is 15 volts. We know that this lamp and this lamp, they are connected in series, so each one of them drops part of this 15 volts. And the voltage dropped here is equals to the voltage dropped here. However, the two lamps here, they are connected in parallel, and this voltmeter measures the potential drop across the parallel connection. Again, once we get the resistance of this lamp and this lamp combined in parallel, we find that there is one resistor whose resistance is going to be half one of these resistors. We've already seen that particular fact elsewhere. So in order to determine the voltmeter reading V, we need to get the total resistance. This is R plus 0.5 R. I'm assuming that the resistance of one of the bulbs is R. So R plus R, 2R. And this R and this R, they are connected in parallel. So the total resistance over here will be 0.5 R. I get that 0.5. I add it to 2R. I get 2.5 R. Using that, I'm able to get the current, the total current flowing, because I need the total EMF divided by the total voltage. So again, let's see what I've already worked out. So let the resistance of one of the bulbs be R, and you can see that the total resistance is given as we have discussed. Total current is therefore equal to 15. I'm using voltage divided by total resistance over 2.5 R. Therefore, the reading of V will be equal to the total current flowing in this branch, which will be the current over here, times the total resistance here. So it will be 15 over 2.5 R, this will be the current, times the resistance in that branch, and we get 3.0 volts. And for that, you're given 2 marks. Let's proceed to question number 4. In this question, we are told that figure 4 shows a negative point charge placed near a positively charged rod. This one is a point charge, which is negatively charged. And here we've got a positively charged rod. We are asked to draw on the diagram the resulting electric field pattern. So there are a few points that you need to remember here, that electric field lines, when they leave a surface, they leave a surface at 90 degrees, and when they enter a surface, they enter a surface at 90 degrees. They point from positively charged body to negatively charged body. So again, I've already drawn this, and this is how it looks like. So the first thing we would be looking for is the direction of these electric field lines. They must point from positively charged body to the negatively charged body. So they enter the negatively charged body. The other point is that they enter at 90 degrees. Notice here that they leave at 90 degrees. Here they curve well, and they enter at 90 degrees. So if you are to draw a tangent here, you must be able to show that actually that is 90 degrees. Very important. And when you are drawing sketches, try to draw sketches which are as neat as possible. Of course, here I've taken my time to try and do this, but even in the exam, it will not be so difficult to draw a diagram which looks exactly like this. So let's go to question 5. In question 5, this is about refractive index and apparent depth. Let's see, we are told that figure 5 shows an object O at the bottom of a beaker full of a liquid. An observer above the beaker sees its image at point X. Of course, this one is common. If you have a beaker of water and you put it on a bench, and at the bottom maybe you had an object, or maybe you could put a piece of paper with a letter marked at that point, then you observe that letter from above here. You will see that the letter or the object is closer to your eye than it actually is. This is how far it is in the liquid. So this is the real depth, but it appears to be somewhere here, so this must be the apparent depth. Now, why do I need to determine those two? I need to determine those two because when it comes to calculating the refractive index, and I have this diagram, it's up to me to realize that I've got a real depth and I've got apparent depth here. And for me to get the apparent depth, I just need to subtract 10 from 40, and I get that the apparent depth is 30 centimeters, while real depth is 40 centimeters. And then I divide the real depth by the apparent depth. Of course, that is what I've already done here. So refractive index of the liquid is going to be equal to real depth of an object which has been put in that liquid over the apparent depth of the same object. And of course, I've already explained this. 40 divided by 40 minus 10. We've got 40 divided by 30, which is 1.33. From the value of this 1.33, we can comfortably guess that this liquid must be water. And let's go to question 6. Question 6 is obviously about radioactivity, because I can see there's a popular symbol here that shows that there is a radioactive source here, and there is this shielding because the radioactive materials must be shielded. And then of course there is a magnetic field. There is a postcard here. When I see the postcard, I think about alpha particles which cannot penetrate a thick piece of paper. And then there are detectors. Detectors are put at positions A, B, and C. Let's see what we are being asked to calculate or to determine. Figure 6 shows a narrow beam of radiation from a radioactive source incident on a postcard. The emergent radiation passes through a magnetic field which is perpendicular to the plane of the paper and into the paper. A detector moved along the line AC detects radiation only at B and C. B and C. Of course, if there is a radiation at point B, we can tell that this radiation is not affected by magnetic field, and we know that those must be gamma rays, because gamma rays, being part of the electromagnetic spectrum, they are not affected by the magnetic field because they do not carry any charge. There is this radiation here which is deflected downwards, and when you use a Fleming's left hand rule with your first finger pointing into the paper and the second finger pointing in this direction, you'll be able to see that the thumb points downwards, and that the thumb is going to point. The second finger, actually the first finger, points into the magnetic field, into the paper, and then we can see that the deflection is downward. So you turn the thumb downwards and you will see that actually the second finger now ends up pointing to the right. Once it points to the right, it tells us that current is to the right. And because we know that these particles are moving this way, then the particles moving this way must carry a negative charge so that current is in the opposite direction. And the particles which carry a negative charge must be beta particles. So again, we are asked to state the types of radiations which are detected, and as usual the answers are given here. Beta particles and gamma rays, these are the ones which are detected. At this point we've got gamma rays because they are not deflected by the magnetic field. At this point we've got beta particles which carry a negative charge. And of course the reason is that gamma rays carry no charge and are therefore not affected by magnetic field. Alpha particles are stopped by a thick piece of paper over here. And of course the other reason is that the particles which are deflected in such a way that they are detected at point C carry a negative charge, and those must be beta particles. So that question was just that easy. Let's go to question 7. In question 7, we are told that figure 7 shows two similar coils P and Q around the end L and M of a piece of soft iron. A steady current passes through the coil. Now you'll be able to see that the winding is as shown. So since this one is a cell, we can tell from the positive, from this positive terminal that current flows this way. It goes below and it emerges on this side as being downwards. When you use a right hand grip rule, you'll be able to see that a south pole is formed here. You'll be able to see that a south pole is formed here. You follow that particular current and you can see that when it comes here again, current goes upwards. And when you use again the right hand grip rule, you'll be able to see that a north is formed here and a south pole formed here. So according to the right hand grip rule here, a north pole is formed here, a south pole is formed there. According again to the same right hand grip rule with the currents now moving upwards here, you can see that a north pole is here and a south pole is here. So L is south, M is south, and there will be repulsion. So state the polarity of the resulting magnet at end L. It will be a south pole. So again, that is how you get that 1 mark. Remember the poles at point M were not required. Let's go to question 8. In question 8, we are told that light from a lamp falls on the cap of a negatively charged electroscope. It is observed that the divergence of the leaf decreases. Explain this observation. Of course, here we need to understand how electroscopes get charged. Okay, and then since it is light which is falling on a piece of metal, we have to know that there are charged particles which are emitted from the surface of the metal, and this of course is about photoelectric effect. So the answer to this is that light removes electrons from the cap of the electroscope by photoelectric effect. This of course reduces the magnitude of the negative charge on the electroscope, and that is why, let's see, negatively charged electroscope, it is observed that the divergence of the leaf decreases. Yes, it is because of the removal of electrons from that negatively charged electroscope, and once that concentration of electrons on the electroscope cap is reduced, it will result in less repulsion between the leaf and the rod, and that is why the leaf collapses. Let's go to question 9. In question 9, this one is very easy. We're told that figure 8 shows an object O placed in front of a diverging lens whose principal focus is F. Okay. On the figure, draw a ray diagram to locate the image formed. And I've already drawn this diagram. So apparently I've used the third rule, or the third rule, which says that a ray of light which passes through the center of the lens never gets bent at all. So I used this one. So the refracted ray is here, and here the refracted ray is here, and you can see that they are diverging. So I just need to extrapolate this one backwards, which I don't need to do because the actual ray actually passed through that point. So that point is already there. The ray that I need to extrapolate is the one which moves like this. And remember, for me to have drawn this, I need to align this point with this point, so that here I draw a dotted line, but here I draw a continuous line. And remember, this ray here is parallel to the principal axis. And that's how you work out question number 9. Let's go over to question 10. Question 10 is about the applications of total internal reflection. Here we've got an optic fiber. This is a very common question. However, let's just read the question together. Figure 9 shows the cross-section of an optic fiber made of two types of glass, A and B. The refractive index of B is lower than that of A. The refractive index of B is lower than that one of A. So once the ray is inside here, it is attempting to move from an optically denser medium to an optically less dense medium. So the first condition of total internal reflection has been achieved, because the first condition is that the ray must attempt to move from an optically denser medium into an optically less dense medium. So we are asked to this part reads, a ray of light enters the optical fiber at P and emerges at Q. Now when it enters here, it does not bend because the angle of incidence at this point is 0. So it just moves through. But that does not mean that the refraction has not taken place. There is a reduction in speed between here, where light is in air, and here it is in glass. So here it is slowed down. However, there is no bending here. But as soon as it strikes this point, we find that the angle of incidence at that point is greater than the critical angle. And therefore, we end up seeing that that ray suffers total internal reflection until it emerges from this medium into the air again at this point. So state the reason why light travels through the fiber as in one above. So it's basically due to total internal reflection occurring at each point where it strikes the boundary between glass fiber A and B. So this is the possible path of the ray, like that. At each and every point here there is total internal reflection. So there is no loss of energy of this ray, because all of it, the energy, the incident energy, is totally internally reflected. So when light strikes the boundary between A and B, it undergoes total internal reflection, because the conditions for total internal reflection have been achieved. And let's go to question 11. Question 11 is about magnetism, where we are told that figure 10 shows the cross section of a conductor held between two magnets and carrying a current out of paper. Again, this is where you use Fleming's left-hand rule. Remember, Fleming's left-hand rule states that if the second finger points in the direction of the current, in this case it will point out of paper, and the first finger points in the direction of the magnetic field, which is from north to south, then the thumb will point in the direction of the force that this conductor experiences. And we can see that once you use that Fleming's left-hand rule, you will realize that the force on this conductor is vertically upwards. So indicate with an arrow on the diagram the direction in which the conductor will move when it is released. So use Fleming's left-hand rule to determine that the force on this conductor will be vertically upwards. And the answer just looks like this. It's just as simple as that for 1 mark. Question 11. State why alternating current is used for transmitting electricity over long distances. This is because it is possible to transform electrical power so that we can have a small amount of current in the cables in order to reduce losses due to the resistance of the cables, because the current will be so small when the voltages are very high. When we come to the consumer, we must reduce those high voltages to lower voltages so that it is safe enough and convenient. And it is transformers which make it possible to step up and step down. So the reason why we generate electrical power as alternating voltage, which of course produces alternating current, is to make it possible to transform or to step up and step down this power or voltages. So to enable stepping up or stepping down of the voltages. So that question number 12 was just as simple as that. Let's go to question 13. Question 13 is about use of diodes in, of course, a rectification, where we are told that figure 11 shows an alternating current AC connected across a diode D and a resistor R. On the axis provided, sketch the output as observed in the CRO connected across R. Of course, here we know that we have the general AC signal. When it comes here, this diode is going to conduct when this terminal here is positive, so it will allow half of the wave to pass through the resistor. But for the other half, when this is positive and this is negative, and current is attempting to flow in the opposite direction through the diode is going to block that, and that voltage will not, that current will not flow through the diode. So this one is a simple half wave rectifier, and the voltage time graph for that looks like this. So this is the section where this part of the AC terminal is positive with respect to this, so current is moving like this, and the diode allows that to happen. As a matter of fact, this symbol here usually shows the direction of flow of conventional current from positive to negative. That's why I'm saying that if this one is positive and this is negative, then current flows in this direction. So that part of the loop is allowed, or that part of the current is allowed to flow through. But for the other half, when the current changes direction, the diode is going to block, and the process is repeated over and over again. So that's how question 13 is tackled. And here we are at question number 14, where we are told that figure 12 shows a displacement time graph for a progressive wave. Displacement time graph. Of course, we can be able to get periodic time from this type of graph because x-axis is time. State the amplitude of the wave. The amplitude of the wave is from this point to this point, so it must be 5 centimeters. Determine the frequency of the wave. The frequency can be determined by, first of all, determining the periodic time. So period is from this point all the way to this point, which is 20 seconds. So it is from one trough to the next trough, or from one crest to the next crest. So 30 minus 10 gives us 20 seconds, or from 0 to 20. Something like that. So since we know the periodic time, we can be able to get the frequency, because the relationship between frequency and periodic time is that frequency is equals to the inverse of the periodic time. Part 3, given that the velocity of the wave is 20 meters per second, determine its wavelength. Remember here, we know its frequency. So since we've been given the speed, we can be able to determine the wavelength. And this is how I worked out the answers. So amplitude A is 5 centimeters. There is no big deal about that. Our frequency is 1 over period, which is 1 over 20, which is 0.05 per second, or 0.05 hertz. Given that the velocity of the wave is 20 meters per second, determine its wavelength. Of course, the wave equation, which says that wavelength is equals to V over F, that is what I used to get the wavelength of 400 meters. Part B of the same question, we are told that figure 13 shows two identical dippers, A and B, vibrating in water in phase with each other. The dippers have the same constant frequency and amplitude. The waves produced are observed along the line MN. This question has perfectly described the conditions that the two waves must fulfill for an interference pattern to be seen here. First of all, they must be waves of the same kind. Like you can see, this is water waves and water waves. They must have a constant phase difference. They must have a constant phase difference. So they are continuously in phase with each other. So the phase difference is 0. The dippers have the same constant frequency and amplitude, so that if they have the same amplitude, then they are going to completely cancel out each other where destructive interference takes place, or reinforce each other where constructive interference again takes place. So the conditions for an interference pattern to be seen along here, especially for light, has been fulfilled. That is where they've taken time to describe all these. The waves produced are observed along the line MN. Let's look at the questions. It is observed that the amplitudes are maximum at points Q and S, Q and S. So this if it were light, this would be the central bright fringe, first bright fringe, and of course between two bright fringes we will have a dark fringe. But this is not light, it's water. So we are going to have maximum amplitude here, maximum amplitude here, and of course 0 or minimum amplitude at this point where destructive interference takes place. Explain why the amplitude is maximum at point Q. It's because constructive interference is taking place. State why the amplitude is minimum at point R. It's of course because the waves are out of phase and the destructive interference is taking place. State what would be happen if the two dippers have different frequencies. If this happens, then the interference pattern here will change rapidly. It will change rapidly, and it will not be possible to observe. It would not be possible to observe this interference pattern that is seen at this point. because it will be changing so rapidly and your eye cannot be able to follow that. So the condition for an interference pattern to be observed perfectly is that the two wave trains must have a constant phase difference, meaning that they must be produced from the same source, because that is how we ensure that they've got a constant phase difference. Okay, let's look at the answers that I wrote down here. Explain why the amplitude is maximum at Q. The displacement of the resultant wave is twice that of the individual displacements because constructive interference is taking place. And why the amplitude is minimum at R. The displacement of the resulting wave is 0 because the magnitude of the two displacements is the same, but one is negative while the other is positive. When you add them together, in order to get the resultant amplitude, you get 0. And state what would happen if the two deepers had different frequencies. The position of the constructive and destructive interference will be changing rapidly, which will be difficult to observe with the naked eye. Hence, no pattern will be observed. Of course, interference will be taking place, but the point at which it takes place is changing so rapidly. That is all about question 14. Let's look at question 15. This is again in current electricity, where we are told that figure 14 shows a circuit in which a battery, a switch, a bulb, and a resistor P are a variable resistor Q, a voltmeter V, and two ammeters A1 and A2 of negligible resistance are connected. P has a resistance of 10 ohms when the switch is closed. P has a resistance of 10 ohms. When the switch is closed, A1 reads 0.1 amperes and the voltmeter reads 1.5 volts. Determine the current passing through P. Where is P? This is P. So if we know the voltage across it and we know its resistance, we can work out the current. Do we know the reading of this voltmeter? We are told that when the switch is closed, A1 reads 0.1 amperes and the voltmeter reads 1.5. So we are going to divide 1.5 by 10 ohms to get the resistance of P. Once we get the resistance of P, we are asked to get the resistance of the bulb. The resistance of the bulb there. So we should know that the voltage across here is the same as the voltage across here, and across the bulb, or across this particular part here, because they are in parallel connection. We've been told that the ammeter has negligible resistance, so it doesn't contribute any resistance to the circuit. So I know the voltage across this bulb is equal to the voltage across P, which is 1.5 volts. Just like we had been given here. The reading of this voltmeter tells us the potential drop across this and across that. And because we know the current which flows through A1 is 0.1, we can be able to use that voltage and that current to work out the resistance of the bulb. So this is how I worked them out. Current through P is equals to potential drop across P over the resistance of P, and I got that. The resistance of the bulb is equal to the potential drop across the bulb divided by the current through the bulb. And again, that is what we have discussed. And that resistance is 1.5, actually it's supposed to be 15 ohms. So just to change to that answer here, because 1.5 divided by 0.1 amperes, this is supposed to be amperes, okay, it's supposed to give me 15 ohms. Let's look at the other part of the question. The variable resistor Q is now adjusted so that a larger current flows through A2. State how this will affect the resistance of the bulb. So we're told that the variable resistance is now adjusted so that a larger current flows through A2, and we want to see how this will affect the resistance of the bulb. Let me see. A larger current flows through A2. It means that more current is going to flow through here, and we know that it's going to produce a heating effect in this bulb, and if it is a filament lamp, then its resistance is going to increase. That is my take on that. And of course, I've given the explanation. This is about calculating the cost of using one bulb of 100 watt, two 60 bulbs, and a 30 watt bulb. Determine the cost of having all the bulbs switched on for 70 hours, given that the cost of electricity is 40 cents per kilowatt hour. Of course, here we need to get the number of kilowatt hours, and then we are going to multiply the number of kilowatt hours or energy consumed in terms of kilowatt hours by the costing. So let's see how that one works out. Of course, the resistance of the bulb will increase. Why is this? The bulb is a non-ohmic conductor. Its resistance increases with the rise in temperature. Current flowing through the bulb will increase, causing an increase in the heating effect of the filament of the bulb. Of course, this word here is an increase. So energy consumed, or the number of kilowatt hours, equals to power times time. Remember to convert that power into kilowatts before you multiply by the time in watts, by the time in hours, in order to get 17.5 kilowatts. The costing is given by the number of kilowatt hours, what we have worked here, times the rating. So 17.5 kilowatt hours times Kenya shilling 0.4, we get 7 shillings. That is the cost of using those components. Let's go to question 16. What does question 16 talk about? This question, of course, is about electromagnetic induction, where we are looking at mutual induction. But let's read the question together. 16a. Figure 15 shows two coils A and B placed close to each other. A is connected to a DC supply and switch B is connected to a sensitive galvanometer. This one is a classical question that is used to demonstrate mutual induction. The switch is now closed. State the observation made on the galvanometer. The galvanometer is going to deflect one direction and the pointer will go back to 0. It's just as simple as that for that first part. The pointer of the galvanometer deflects briefly and then returns to 0, or center of the scale, because a galvanometer has got its pointer at the center of the scale. So when there is no potential difference across it, the pointer is always at the center of the scale. The pointer is always put at the center so that it can either deflect to the left or to the right, showing the direction in which current is flowing through it. We've been asked to explain what would be observed if the switch is then opened. Of course, it will deflect in the opposite direction and then come back to 0. It will deflect in the opposite direction and then the pointer again comes back to 0. Why does that happen? This is because the magnetic field that had already built up is now collapsing. You see, the reason why we have a deflection here is because upon switching on, the current in coil A is going to increase from 0 to a maximum value within a very short time. That will cause the magnetic field around it to change or to build up. Once it is changing or building up, it's going to cut coil B, inducing an EMF in it. This EMF will create an induced current to flow because the ends of the coil are connected together via this galvanometer. So the galvanometer deflects that induced current. So that is what happens when we switch off, as we've been asked to answer this question. When we switch off, the magnetic field that had built up now collapses. As it collapses, it cuts the turns in the opposite direction. That is why the induced EMF is in the opposite direction. And of course, this one is a calculation on transformers. The primary coil of a transformer has 100 turns and the secondary coil has 200 turns. The primary coil is connected to 240 volts AC supply. Explain how an EMF is induced in the secondary coil. Of course, this is by the same process, by electromagnetic induction, where this alternating current causes a changing magnetic field in the primary. That changing magnetic field is going to link or turn or cut the secondary turns, inducing an EMF. Determine the secondary voltage. Of course, here we use the turns ratio where we have Vs over Vp is equals to Ns over Np. Efficiency of the transformer is about power input divided by power output expressed as a percentage. Again, let's look at the answers which I gave. So over here in the first part, the point of the galvanometer deflects briefly in the directions opposite to that in part A and then returns to 0. That is the observation. So of course there is 1 mark for that observation. Now why does it happen? The EMF induced in the coil during switching off is opposite because the magnetic field is collapsing, and therefore the magnetic field due to the first coil is cutting the secondary in the opposite direction, and that is where the EMF induced changes direction. So here we are explaining how the transformer produces an induced EMF in the secondary coil. The alternating current in the primary coil produces a changing magnetic field. The concept of the changing magnetic field brought about by the AC is important. Remember, in one of the questions earlier on, we talked about why why power is generated as alternating voltages. It is to enable the process of stepping up and stepping down, because it's only alternating current which can produce a changing magnetic field. This changing magnetic field is going to link the turns of the secondary, inducing an EMF in it which causes induced current to flow. Of course, the turns ratio is as given here. When you substitute, you get the output to be 48 volts. This appears to be a step down transformer. Yeah, of course it's a step down. I had taken these 1000 turns as being the turns in the secondary, but actually they are in the primary. So the voltage which is induced will be 5 times smaller. So if you divide 240 by 5, you're going to get about 48 volts. Or you can use the turns ratio as I've shown it here. Either method is okay. Efficiency is power output divided by power input expressed as a percentage by multiplying by 100. That means power in output is current in the secondary times voltage in the secondary. Power input is current in the primary times voltage in the primary. And when you manipulate those figures, you get this transformer to be 80% efficient. Let's look at question 17. Question 17A, we are told that figure 16 shows a graph of magnification against object distance for an object placed in front of a lens of focal length 20 centimeters. And this is what we get. Using the graph, state the effect on the size of the image when the object distance is increased from 25. So the object distance is increased from 25 centimeters. The effect on the size of the image, what happens to it? You can see that the magnification reduces. Actually, the magnification is going to reduce as we increase the object distance. So the size of the image is decreased. Why? Because the magnification is going to reduce, or magnification is reducing. Remember, magnification is the ratio of the size of the image to the size of the object. If magnification is 2, for example, that means that the image is twice in size to that of the object. But here you can see magnification is reducing in size, and that means that the size of the image is decreasing. Let's look at part 2. Determine the distance between the object and the lens when the image is the same size as the object. Again, when we go back to the diagram, we are going to check where the magnification is 1. That means that the object distance equals to the image distance. So the object distance is actually 40 centimeters. So since the object distance is 40 centimeters, we can be able to determine the distance between the object and the lens, which means object distance. All right. Part 2, determine the image distance when the object distance is 25 centimeters. Again, we use the graph for that purpose. So let me see what I wrote for this particular page. So here magnification is equals to 1, meaning that object distance equals to 40, and I've shown you how we determine that from the graph. Now since magnification is 3.5 when object distance is 25, again we can confirm this from this graph here. When image distance is 25, object distance is 25 rather, the magnification is 3.5. All right, that's how you make use of that. So since magnification is 3.5 and magnification is equals to image distance over object distance, which is v over 25, we can get our v to be 87.5. So this is one of the expressions that can be used to calculate magnification. Although magnification is defined as the ratio of the image distance to the object distance, it can also be worked out as image distance divided by object distance. So in question 17, this part B, we are told that figure 17 shows an object O placed in front of a converging mirror of focal length 15 centimeters over there. So there is an object over here, and I can see that it is at twice the focal length, or at C. So definitely the image is going to be of the same size and it is formed at the same point. But you must show the use of these rays. One of them is initially close to and parallel to the principal axis. It will be reflected through F. The one which passes through F will be reflected parallel, and where these two reflected rays, this one and this one, meet is where the point on the object where they came from is going to be formed. So let's look at part C. State why parabolic reflectors are used in car headlamps. They're used in car headlamps because if a bulb is placed at the principal focus, it will produce a parallel beam of high intensity, because this is our intention, that the beam produced from the headlamps should be intense and parallel, not scattered in all sorts of directions. And let's look at question 18. What are we told in question 18? We are told that figure 18 shows parts of an X-ray tube, and this one is a standard question. So you should be able to draw an X-ray tube, name all the parts, and state their functions. Let's see. Explain why a potential difference is applied to the filament. This small potential difference here is applied to the filament so that the filament can heat up the cathode, which will produce electrons by thermionic emission. So the purpose of that potential difference is to produce a current flowing through the coil, which is going to become warm, heat up the cathode, and the cathode produces electrons by thermionic emission. Part 2. A high potential difference is applied between the cathode and the anode. The purpose of this extra high tension over here is to accelerate the electrons between the cathode and the anode so that they strike the anode with a very, very high speed. So why that potential? That high potential serves to accelerate the electrons, giving them a very high speed, which is necessary for production of X-rays when these cathode rays hit a metal target. Again, state why most of the tube is surrounded by lead. It is surrounded by lead because we want to absorb any stray X-rays. They are absorbed by that lead shielding. This one makes it safe for those personnel who are operating the X-ray tube. It also makes sure that the patient is not exposed to high doses of X-rays. So it's only this part which is put under this window that gets exposed to X-rays. Otherwise, the rest of the body of the patient will not suffer any overexposure to X-rays. And these were the answers. Potential differences apply to the filament because we want to heat the cathode, which will produce electrons by thermionic emission, a high potential difference is applied between the cathode and the anode. The high potential difference is needed in order to accelerate the electrons produced at the cathode to a very high speed before they strike the anode, because that one is a condition for X-rays to be produced. Most of the tube is surrounded by lead to absorb stray X-rays produced at the anode. And let's look at part B of that question. State how the resulting X-rays are affected by increasing the potential difference between the anode and the cathode. You see, this is the accelerating potential. The cathode rays will have a much higher speed. They will strike the target with a much higher speed, and therefore they are going to produce X-rays of a much higher frequency or more intense X-rays. So the energy of the X-rays will be increased. And here we've got a calculation. So let me take you through these. So for part 1, when this voltage is increased, the speed of the cathode rays increases. And remember, cathode rays are just fast moving electrons. When these high speed electrons strike the target rather, X-rays of high energy or strength are produced. Now let's look at this part. Light of frequency 7.5 by 10 raised to power 14 strikes a metal target. So we are able to calculate the energy of the incident photon. This energy of the incident photon, which is equals to HF. How is it used? When that light strikes a metal target whose work function is this, so this energy of the incident photon is used to provide the necessary work function, and then it uses the rest of the energy to give kinetic energy to the electrons. So you must be able to use this Einstein's equation of photoelectric effect. Energy of the incident photon is equals to the work function plus the kinetic energy. What this means is that this energy of the incident photon is shared between providing the work function and using the excess energy to give the electrons the necessary kinetic energy. The question here is to determine the kinetic energy of the emitted photoelectron. So it was just a matter of substituting these inside here, and we get the kinetic energy as being 0.9725 by 10 raised to power 19 minus 19 joules. And that brings us to the end of this paper. I want to thank you for being there with me all this time. If you're seeing this video for the first time and maybe you're not a member of my YouTube channel, take time and subscribe. You can also share this video with your friends. I will really appreciate that. And then the last thing you can do is put a comment below, maybe requesting that I do a particular paper or I teach you a particular skill, like for example practical skills, because my next video I'm designing a video where I take you through a practical paper where we'll discuss what you're expected to do if you collect the data. When the graph is being marked, what do they look for when they're marking your work? And I hope that video will be of much use. But meanwhile, share this video and give it a thumbs up. Thank you and see you next time.